Okay, let's move on to the continuous random variables. So we talk about discrete cases, and we also mentioned one such continuous random variable, which is the uniform distribution. Uniform distribution in the continuous setting means you actually, the density function is a constant, is flat, and is over the interval where it is the uniform distribution is. So for uniform distribution, you have to specify the starting point and the end point, all right? So just like this. This is 0 and this is 30. So you basically, for uniform distribution, you have to have two parameters. That is the starting point and the end point. And then the density function is actually very easy to deduce because you know it is flat, and you know the area under the density function is equal to 1. So if the width here, or if the length of the interval that it is flat, so the area is equal to 1, so it forces the height has to be 1 over 30. All right, so and if the starting point is A and B, so the length of the rectangle would be B minus A, and as a result, the height of the rectangle has to be 1 over B minus A. So things are actually pretty easy. And another thing that the uniform distribution is, the probability of an interval like 25 to 30 depends only on the length of this interval, all right? So it only depends on the length here, which is 5. It doesn't depend on where you start, whether you start from 10 to 15 or you are starting from 25 to end at 30. It is because it's uniform. The probability over any interval is basically the area of the under the curve over that interval. And that is because the height is already a constant, so the area actually only depends on the length of the interval that you are looking at. And that probably is the reason why people call it uniform. It doesn't really depend on where you start. I mean, so you have no preference as to where the starting point is, as long as the interval length is given to you. Okay, so that's about the uniform distribution. The second continuous random variable that we introduce will be the exponential distribution. And then, of course, the third one would be the normal distribution, as in this chapter. I think in the subsequent chapter, chapter 5, we'll introduce you some other distribution functions, but we'll be basically a user of that rather than doing explicit calculations. So I think one of the main slides actually is at the end of this random variable, and let me go to that first. Okay, so applications of the exponential distribution. This is the crux of the whole thing. It's usually used to model, here it says something here, but I'll just say time to an event, all right? So from the start to a certain time of your event, here is talking about successive events, so you can always think of when an event happens, then that is your starting point for the time of the next event, all right? So you can think of it this way. And the time of event, usually we are thinking of some of the example we are going to go through would be time to failure. For example, the light bulb is not working, or some electrical appliances. Now this is, for electrical appliances, it is actually a little bit of a stretch, because in engineering, I think people would not believe in exponential distribution because there is a property that we are going to talk about, is the memoryless property. That means the appliance or the component does not age, all right? which is not true in a lot of electrical appliances. If you have been using your washing machine for 5 years and then you are asking whether it will work for another year, the memoryless property means that it is just like you are starting your washing machine new and then asking whether it will work for another year, which is unlikely, all right? So replacement in the engineering area, replace it with Weibull distribution. So that is other things that we are not covering. But somehow for light bulb, I don't know the physics or the engineering enough, but usually it is quite a good model. It is not a very good model only at the very start when you switch on the light bulb. Okay, if this little period of time the light bulb survives, then the time of the light bulb to fail seems to fit the exponential distribution fairly well. All right. So anyway, you can take it as one of the introduction to this. Time of an event also refers to, say, the time of arrival of a phone call, and that is basically used, or time of arrival of a customer at a store, or a file or instruction at a server. Okay, so it's the basically arrival time of certain things. All right. So it is quite often used as exponential distribution to model this. The main reason is because it has this nice property, the memoryless property, because we can invoke a certain independence distribution, certain independence technique there. But if it is not independent, then the problem will be very difficult in many applied problems. Okay, but probably you won't encounter this. But let's go to the exponential distribution. So the exponential distribution, the density function is written in this way, and this is called the parameter lambda. Now, but I want to warn you, because different people have a different way of putting the lambda. Some people write it as 1 over lambda, e to the powers minus x over lambda. So their lambda is 1 over your lambda here. All right, so there is a bit of an ambiguity. So the better way of saying the exponential distribution, of course, this is after, so it's to specify the mean. All right, once you specify the mean, then your lambda will be specified. All right, whether you write it in this way, the way that we write it here in this module, or some other people write it 1 over lambda. So this is either you specify the mean, and so for which you can solve your lambda, and then the lambda is in this form. Or people say the lambda is the rate of the exponential distribution. Now over there, the thinking is actually the time period is actually fixed, for example, a certain time period, and then the rate is how many arrival per time, and so it's the time period over your lambda there. All right, so here, if the rate is smaller, then your mean is bigger. So that means you don't have to wait too long, or you have to wait longer. Say, for example, your lambda is smaller, then your expectation is bigger. So it means that you have to wait longer. All right. Smaller lambda, that's why they call it a rate, because smaller lambda means the rate of arrival is slower, and as a result, you have to wait longer. All right. So now another thing that is interesting. For the exponential distribution, if I think of the standard deviation, not the variance, it would be the square root of this, and it would be 1 over lambda. And here, the exponential distribution, the mean and the standard deviations are equal. All right. This is in contrast to Poisson distribution, where the mean and the variance are equal. All right. Okay. Now I want to caution you, if it is exponential, the mean and the standard deviations are equal. But if you know a certain random variable and you do not know about the distribution, but all you know is the mean and the standard deviation are equal, it doesn't mean the random variable has to be an exponential distribution, all right? Because basically, you are summarizing the density curve into two numbers, so it would be too much to expect that it's a characterization. Okay, so let me show you the graph. This is the density function, e to the power minus x. If you change it to the usual one, lambda times e to the power minus lambda x, it would be the same shape, except that the starting point is a little bit different. Okay, so, sorry? A bit larger. Huh? Oh, okay. All right, thank you. The random variable is living on the positive x, so we just show this. Now, depending on this, it means that when x is 0, it is 0. All right. This is immaterial, but I just want to show you. And so this would be there's a hole here, lambda e minus. This is lambda, and so as a result, this is this. It does not cross the x-axis. All right. So that would be this. And of course, the density function is 0 here, and then like this. Now, this is just one version. And then another version would be like this. And so we won't have this. And so as a result, the only difference is this is not a hole, but this is now a hole here. So there is just a 1 point difference. All right? We know that it would still give you the same distribution function. The density function, they are different. They are different at only 1 point, but the difference at 1 point doesn't really matter, all right? Because we are more interested in the area under the curve, so just 1 point change will not change any of the area. All right, so everything is look like this, all right? It's just depending on your lambda. If your lambda is bigger, then it's just it bend a little bit faster. But it just has to do with our scale. So if you think of x in terms of lambda x, then it would be the same as e to the power minus x. So they all follow the same shape, all right? Okay, so and we are interested in the probability that the exponential function distribution is following falls within the interval AB. Now, this is a continuous random variable. It doesn't really matter whether you have an equal sign at one of the endpoints, so it doesn't really hurt, all right? Now, I think if you refer to the tutorial, when we set the questions for discrete random variable, when we are asking for the probability of the interval, we have to be careful, especially if we do not write these expressions. So we will say inclusive of both endpoints or whatever, all right? So we just have to be careful because for discrete case, have an equal sign, then you include the point probability of x equal to a into it. So the distribution function of this is very easy. This is this one. So I think if you have some physics background, this is the reverse of your exponential decay of whatever things that you are looking at. And here it is like this, all right? So, it is always under 1, okay? So this is the density function, whereas this is the distribution function. So you have a 1 here. Okay. Let me make it a bit smaller. Okay. So it would be something like this. It would be 0, and then it is actually like this. All right. So again, it will never cross or even touch this line, but it's just getting closer and closer. So if you look at it upside down or this way, then this is your usual, exponential decay. All right. Okay, so the exponential function all take this kind of form. Okay, now we're addressing this. Suppose that the length of a phone call in 10 minutes is an exponential random variable with parameter lambda equal to 1/10. That basically means within one time unit, you have 10 phone calls. All right. Someone arrives immediately ahead of you at a public phone booth. Find the probability that you have to wait more than 10 minutes, between 10 to 20 minutes. So this problem does not have any appeal to you anymore. I mean, you guys, everyone has your own phone. I mean, why should you wait for this? All right. So this is this. The probability that x is bigger than 10, that means you have to wait longer than 10 minutes, will be just simply this. And now the lambda is given to be 1/10, and this 10 is from here, so it is just e to the power minus 1, and it is something like 37%. And if you need to wait between 10 minutes to 20 minutes, so this is just this, and so it would be just plugging into the formula. And for F20, because I still have minus 1/10, but now I have to times 20, so as a result I have minus 2 here, and this has been found earlier. So this worked out to be something like 23%, all right? So the R code is this. Again, this is the stamp, all right, of the distribution, so it's exponential. And the P stands for the cumulative distribution function from the left-hand side, all right? So P, always use it for this purpose. This stamp for you to change the distribution. And X is the one that you are looking at. And now, if you don't need to type in the word lambda, but if you type in the word lambda and then equal to certain things, then the position of where you put, whether it's the second coordinate or the first coordinate, doesn't really matter because you have already told R that this is the lambda. But if you don't type in the lambda like this, then you have to follow the order of your input. All right, so 10 would correspond to X, and then the R software would take 1/10 as the lambda. All right, and so this is just this. All right. Suppose that the failure time t of a system is exponentially distributed with a mean of 5 years. So everything is measured in years now, all right? So what is the probability that at least 2 out of 5 of these systems are still functioning at the end of 8 years? Now this is a very important example because this example actually embeds 2 distributions in the problem. The first one is to calculate for one particular system, what is the probability that it would survive or it would die before 8 years, all right? So this is this. But now here it is asking, but if we are looking at 5 of this, okay, I think this is not spelled out very clearly. These 5 of things are acting independently of one another. And so we are asking at the end of the 8 years, these 5 systems, I want at least 2 of them to survive beyond 8 years. So what it means is that I have 5 systems or I have 5 trials, and I want to have at least 2 trials that is successful. All right. So success here corresponds to the system is able to survive more than 8 years. All right. So it would be a binomial distribution. So the question here look innocent, but actually first would require you to do the exponential distribution first, and then apply your binomial distributions. So this is how this slide is solving the problem. So the first thing is to handle one system at a time. So we were told that expectation of t, on the average is 5 years, and then so the rate is 1 out of 5 years. And so this is our notation in this module, but the notation is not universal, all right? So as a result, the probability of t bigger than 8, remember that e to the power minus lambda x, and so lambda is 1 over 5, and x is 8. So I calculated it, it is equal to 0.2, all right? So now, basically, now I look at one system at a time. So I declare this system is a success if it survives more than 8 years, and a failure if it is it dies within 8 years. So and now I have another random variable that coming in, even though the questions didn't ask for it. Okay, so it is embedded into the inside the questions. So x represents the number of systems out of the 5 systems still functioning after 8 years. So assuming everything is independent, the 5 systems act independently of one another, then x would be a binomial distribution with 5 trials because it corresponds to 5 systems. And then success probability is only when that particular system survives more than 8 years. So here, this would be this. So we just plug it into this into the binomial. So this is 26, something like 26.3%. Yes?
I was just wondering, for the exponential distribution, the function you gave us for like f of x is equal to, if t was equal to 8, lambda, there'd be a lambda out in front of the e. So why is when t greater than 8, you just drop the lambda?
Oh, this is the lambda here. Oh, this is the tail probability. So this is not referring to the it's not referring to the density functions. So in the density function, I have a lambda here. All right, but in the distribution functions, the lambda disappear here. Yeah. All right. It is easier to remember, this is about the left area, what we call the left tail probability. But it would be easier to remember if you remember it the right tail, because the right tail area would be just e to the powers minus lambda times x, all right, if this is x. All right. So, and that is, in the problem, lambda is 1 over 5, and then x is equal to 8 here. So, they were asking about this thing. Am I answering what you're asking? Any other questions here? Because in the tutorial, you will see this kind of questions that we basically ask 2 probability calculations. One is either exponential, and then after we have introduced the normal, we will ask something like this. For example, like this, one of the tutorial problem of the week after next week is this. You have an automated machine that give out a certain amount of drink, say 200 ml, say of Coca-Cola. and the cup that they use is 230 mils. Now this is the machine subject to some error in giving out the Coca-Cola. And so it is 200, that is the targeted amount, plus or minus a certain standard deviations. Now, occasionally, the machine is giving out too much, and as a result, the cup might overflow. All right, so this kind of question, and so what we are interested to ask is, on the average, suppose I have 100 cups in the machines, how often I will encounter situations that certain a number of cups that will be there is a spillage there. All right. Now, of course, if you are able to tune the machines, of course, you want to tune the standard deviations a little bit lower. Or in order to avoid overflowing, then you just have to use a slightly larger cup, to avoid it. So all these are having to do with surface. Another thing is like this, that happens. If you buy a loaf of bread, they always tell you how heavy it is. Now, if I don't know whether you go home and weigh it. Some people do, and now when they say it's 400 gram, you don't expect 400 gram exactly. You might have 400 gram plus or minus something. But if you go home and weigh it often enough, and then you find that always you get the short end of 400. You might wonder, actually, they tell you it's 400, but they actually giving you less, slightly less, maybe 380. Now, you might complain to the consumer, the case, right? I forget about the long form. Yeah, anyway, so this kind of things happen, all right? So because you are guessing whether the manufacturer is actually trying to give you less, all right? So that is unfair practice. So many of this problem is actually embedded into first calculate per item what is the probability, and that part will be a model, like in this case is exponential. But for Coca-Cola, the machine thing, it would be a normal distribution. And then, but this is not, we are interested. But we are interested in how often we have something weird happen, all right? This is good things. Of course, your system lasts longer. Talking about this, this has been my experience when I buy quite a number of laptops over the years. And usually the warranty is 2 years. And many times I found that slightly after 2 years, the machine doesn't work. So I was wondering, the manufacturer is really good in the quality control. Very close to 2 years, all right? But that is my experience. Okay, so now you have to do, first of all, calculate the exponential distribution. Yes. Oh, I'm too excited about the Coca-Cola thing. So anyway, this is, we have to calculate two probability. And for this, using R, it would be, because we are computing the right hand tail, and this is always giving you the left part. So you have to 1 minus, all right? Now there is a command because, but this is not necessary. You can round it too. You can impose another function called round, R-O-U-N-D, and then comma, and 4, let's say, means that I round the number into 4 decimal places. So they would do it for you, all right? Now this is after you calculate this per system. And now I'm interested in, I have 5 systems, and now I want it to be at least 2. That means at most 1 will survive more than, this is the opposite of the problem that I'm looking for. I'm looking for at least 2. And now this is at most 1, all right? So I have to take 1 minus the opposite, all right? And so this worked out to be 26.3%, all right? Now this is the interesting property. that why in a lot of there is actually a branch of probability called queuing theory, and this is one of the heavily used model for the memoryless property. Now there is a parallel between this and also the geometric distribution. It's the same situations, because in a way the geometric random variable is a discrete version of this continuous version of the exponential distribution. Okay, now let me interpret this. Suppose we are thinking of X is measuring the time to failure of say a certain system or the light bulb. So you already know that the light bulb has been working until time S, all right? And you wanted to ask whether the light bulb will work for another t unit of time, all right? So, so this is the probability, the conditional probability that we wanted to compute. Now, a very simple calculations in the next slide shows that this left-hand side, which is a conditional probability, is actually equal to this, meaning that the S has been forgotten. The age of this light bulb has been forgotten. So that is why they call it memoryless. As if you are buying a new one, and then you are asking whether this new one will work for at least time t, all right? This is good news for a lot of us. I mean, it means we are ageless, all right? So, so probability of x bigger than t, this is the general t, and so it worked out to be e to the power minus lambda t, something that I mentioned. This is the right tail. It is easier to remember the right tail. The left tail is just 1 minus this, all right? And so as a result, the left-hand side of the memoryless property is saying this. This is the usual step. You unconditionalize the whole thing. So probability of x bigger than s plus t and probability x is bigger than s over this. Now the numerator is this. This is a subset of this set. All right? Because you insist that it has to live beyond s plus t, then of course it must live beyond s, right? So as a result, this is being a subset of this, so the intersection of this will be just itself. So this is the simplification here. And now we just quote our previous calculations. This is, we are just changing the t to s plus t, and then the denominator change it to s. And you can notice that s disappear after the cancellation of the factor. And so, but this in itself is also equal to this, all right? So that is why we established this. Now, so the remark here, just repeating what I have mentioned. The above states that the exponential distribution has no memory in the following sense. Let x denote the life length, the lifetime of a bulb, given that the bulb has lasted s time units. So this is given, all right, condition on this. Then the probability that it will last for the next t units, and this is the event that I'm interested, okay, but I condition on what I already have, the information. And it's the same as the probability that it will last for the first time t units as if it is brand new, all right, so. Okay. Okay, so here. Now this is a little bit, I mean, a bit stretch, the modeling here, because we know cars actually age. I mean, that's why in Singapore you have to, we are given only 10 years for the car. If the car doesn't age, then the policy wouldn't make sense, all right? So, but let's assume this is memoryless. Jones figures that the total number of thousands of miles that an automobile can be driven before it would need to be junk is an exponential random variable with parameter 1 over 20. The unit is measured in thousands of miles. Okay, when I was looking at the slide, only then I realized that the unit is measured in thousands of miles. Smith has a used car that he claims he has driven only 10,000 miles. If Jones purchases the car, what is the probability that she would get at least another 20,000 additional miles out of it? Repeat under the assumption that the lifetime mileage of the car is not exponentially distributed, but rather is uniformly distributed over here. Everything is in thousands of miles, all right? So this is just a modeling. So again, I'm interested in that it work more than 20,000 miles. So, and because of the memoryless property, the Jones bought over this guy's car, bought over Smith's car, would be as if it is new, all right? Well, if it's new, then she wouldn't use the old price to buy from Smith, right? I mean, so Smith will undersell his car. And this is this, all right? So this is e to the power minus 1. We have this just earlier. It is about 36%, right? Something like that. So if the lifetime distribution is not exponential, but is uniform over 0 to 40 in 1,000 miles, then the desired probability is given by this. So this is almost the standard. You unconditionalize the problem, and so it would be a ratio of 2 probabilities. The numerator is actually t bigger than 30 and t bigger than 10. But if t is bigger than 30, it implies t bigger than 10. So t bigger than 10 can be dropped, all right? And so here, this is from the uniform distribution. Because the whole interval is 40, so now from 30 to 40, the length is 10 out of 40, the total length. So this is 10 over 40. And from 10 to 40, the length is 30. So it is 30 over 40. So as a result, it is 1/3. So the probability here is pretty close. This is 36 and this is 33. But I believe either of this is, not very reasonable modeling. But it is an academic example anyway. So this is the light bulb thing. The lifetime of an ABC light bulbs follows the exponential distribution. If the average lifetime of ABC light bulbs is 3 years, what is the probability of an ABC light bulb lasting longer than 4 years? So this is just the exponential calculations. And then what is the probability of a light bulb lasting another 4 years, given that it has already lasted 4 years? So this is basically a test on memoryless property, all right? So the answer would be the same, all right? So expectation of x is equal to 3. So the lambda that you have to fit it in is 1/3. And so if you remember, probability of x bigger than small x is e to the power minus lambda x. So you can just get it here right away, and it will work out to be 26.4%. Now the probability of the light bulb lasting another 4 years, given that it has already lasted 4 years, well, because of the memoryless property, this old light bulb is actually acting as new, all right? So something that we have done earlier. So it's the same answer. Okay, so I think it would be a good time to have a break. We'll introduce the normal distribution. Now the normal distribution appears everywhere. There is a reason for it, but that would be more or less explained in the next chapter, and that is the famous central limit theorem. The term called central limit theorem was around 1930 when people discovered it. The discovery is actually quite gradual. It's around 1600. The first guy who proved it is de Moivre, who is actually a consultant. I mean, for the gamblers going to the gambling den, he make a living by that. De Moivre actually make a lot of contribution to other branch of mathematics. And he was actually approximating a coin toss when the coin is fair. Laplace, I think in 30 years or a bit later, extend the binomial, the normal approximations of the binomial for general P, all right? So, and then people started to, the complete theorem is actually proved in around 1930s. And the probabilists at that time think that this is the most important theorem, and that's why it's called central, all right? So it's the most important limit theorem. So this central limit theorem explains why the normal distribution appears everywhere, all right? So after the break, we'll go to the normal distribution. So you please come back at 10:50. Yeah, 10:50. Okay, this is the most important continuous random variable that we have, and sure enough, it just appears everywhere, and it has a different name. The more mathematically inclined people will call it a Gaussian distribution because it's coming from Gauss. In the public, people think of it as a bell shape, but of course, I mean, by looking at the shape, it's not so easy to decide whether it is normal distribution because the t distribution will also look like a bell shape as well. So when we introduce the t distribution, you will see the middle part of where we are focusing will be almost the same in terms of the shape. It's just a little bit lower or higher. So that varies. Okay, this is the form of the density function. So this is exponential function, and this is a square here, and over 2 sigma square. Okay, there are two parameters to specify a normal distribution. So when you say it is a normal distribution, you haven't fixed it yet. You have to tell people what is the mean of the random variable of the normal distribution, which is mu. And then this is our notation. We always write the variance in the second parameter, all right? Now, this is not universal. I do encounter some other textbook, which is on the rare side. They just write sigma, all right? So you have to, I mean, watch out for the possibility that people say this. But of course, the best things to specify things is to spell out the mean and the variance rather than just a parameter, mu and whatever, all right? So now the sigma is here. It is not a square or it's under square root. X minus mu will be in the unit that you are measuring. Suppose you are measuring, say, in our height, it would be meter square, and the sigma square will also be meter square. So this is actually a real number. It is unitness, all right? Now, another thing to notice is that this is x minus mu. When x is either on the, it is symmetric function at mu, all right? Because whether it is x minus, whether it's 2 units on the right-hand side of mu or the 2 units on the right-hand side of mu, it would be just differing by +2 or -2. But since you have a square here, the left side and the right side disappear, the difference, all right? So it is symmetric at the mu. And mu is going to be our mean, so it would be symmetric at the mean, all right? And the things actually start to drop because exponential function is, I have a negative sign here, and this is always positive. So the things actually start to drop. Not only it drops, but it drops very fast because of the square term and the exponential term, all right? So it is actually faster than exponential decay because it's not e to the power minus x, but it's e to the power minus x squared. So it's dropped faster. So a characteristic, of course, this is just qualitative, visual, is that the tail, the very upper end of the tail and the very left upper lower tail is very thin, all right? So I think in some of the modeling in your future, people talk about heavy tails, thin tails, they are referring to this. The normal is actually characteristically very thin tails, all right? We will see it very soon, okay? The bell shape is just a qualitative statement. We can't really tell it is really the normal density by looking at it, all right? But is okay, is always positive. So the density function is always positive. Now, when we are using normal distribution, that is when I had trouble when I first learned this. People use normal distribution to model our height, but the random variable can take negative values, so it doesn't make sense. But the fact that now I think is make okay sense because the normal distribution dropped very quickly. So suppose our mean of the height is say 1.7 here in Singapore for male. I mean, I make it up, all right. So anyway, I mean, plus the standard deviation is say 10 cm. Okay, it's top of my head. All right, no substantiation. So basically, everything is lived within 3 standard deviations from the mean. Okay, the normal distribution. So so if you have 1.7 meter and then minus even 3 standard deviation, minus 30. So almost you will never have a negative height. So so that is still a good modeling. All right. But this is the actual situation. It's always positive. It is symmetrical at the mean. All right. The plot will show it, and attains its maximum value at the mean. Now. The maximum value, we haven't introduced a term called the mode. The mode or the maximum value, especially this is interesting for discrete random variable. If you were to stock up your shoes, I mean if you are selling shoes, you stock up more for the mode of the shoe size. That is the shoe size that is most common to your potential customers. So the mode and the mean. And actually, the median is also the same because the median is a halfway point because it is entirely symmetric at mu. So at mu, it is also the median. So for normal distribution, mean, mode, mu, mean, median, mode are all coincide. All right. Now the normal curve approaches the horizontal axis asymptotically as we proceed in either direction away from the mean. It is actually very fast, asymptotically, but it always stays on top of it. 2 normal curves are identical in shape if they have the same sigma square. They are centered at different positions when their means are different, all right? So as sigma square, that means as the standard deviation increases, that means there is more and more variations because the area under the curve has always to be 1. So if you have more and more variations, the height of the curve has to come down because that would compensate back. I mean, it's expanding sideways. All right. So this is not an easy integral. All right. So if you're really interested to want to do it, people actually consider a double integral of this. And then use polar coordinates for transformation in order to prove it here. Okay, so this is the bell shape, and the sigma here is just whatever the person could plot it is. Okay, and this is the curve. So this is the bell shape. And in fact, it drops to 0 very quickly. Now, in fact, later on we can demonstrate this. The area between mu minus sigma to mu plus sigma, meaning that the area that is within 1 standard deviation is 68.3%, all right? And now, so almost like 2/3 of the area is lying between 1 standard deviations around the mean. And then how about 2 standard deviations? It is almost like 95%. Now, that is why people are making a guess why we always use 95% confidence interval or hypothesis testing. It's always 5%. It is because if it is everything is under normal distribution, then the 2 standard deviation is a nice number. Okay, the 5% actually corresponds to 1.96 sigma, but they round it to 2 sigma. And then how about 3 sigma? 3 sigma deviations would be 99.7%. All right, so if you have a data with 1,000 points, if it is coming from a normal distribution, you only expect 3 numbers from your 1,000 data point to be outside your mean plus or minus 3 standard deviations. So a lot of things are actually captured within there. All right? And so this is also the mode, the place where it is, has the highest probability, and so on and so forth. Okay, so maybe I'll demonstrate the calculations because I don't think it was included in the lecture notes. So, and this is one of the rules that people usually remember. So the stem of the probability of the normal distribution is NORM, normal. And P is the cumulative distribution function from the left-hand side. So I want it to be 1, up to 1 standard deviations. And then the mean is 0. The third number is the standard deviations for R. Okay. And now this is all the way from minus infinity to 1. So I want it to be something sandwiched between minus 1. All right. So this is this. So this is the normal distribution within 1 standard deviation from its mean. So this is 68.3%. How about 2 standard deviations? Okay, so this is 95.4%. So people think of it as 95. Okay, for 2. So that is why it is. Of course, we don't know why people pick 95% or 5% in a lot of hypothesis testing. It has been now a tradition. Okay, and how about 3 standard deviations from the mean? So this is 99.7. So in a lot of textbooks for social science, they actually have this rule called 68, 95, 99.7 rules. All right, and that is the basically spelling out within 1 standard deviation, within 2 standard deviation, and within 3 standard deviations. So this is actually sort of like a first check whether the normal, whether it is reasonable to have a normal distribution. All right. Suppose you have 1,000 data points and then you have 200 of them outside your 3 standard deviation. Then you will have a hard time to argue that it is likely to be normal distribution. But if you have 10, well, you may still close one eye that it is. It is normal distributions. So this is a rough guide for having this. Okay, the normal distribution and Gauss. Gauss is a mathematic prodigy. All right, I think you must have heard a lot about him. And he has a lot of contribution, not just in this case, but mostly in number theory as well as some other thing. He came up with this because he was actually looking at the error of the astronomers who are measuring the position of the stars. And so that comes the normal distributions. Okay, this is how he looks like, all right? I think Gauss is somewhat like in mathematics, probably somewhat like Einstein in physics. So this is the standard normal here, all right? So the notation is quite often used. This is called phi, phi. This is a lowercase of the Greek letter phi, and this is the uppercase of the Greek letter phi. All right. So as a result, so we are still consistent with our usual notation. Uppercase refers to cumulative distribution function, and then lowercase is the density. Now, unfortunately, this integration is we don't have a closed form formula for this. A closed form formula means you have just a function like sine x or cosine sine x, that kind of thing, that you can evaluate. The evaluation is actually done by numerical means, all right? So they basically divide the interval into a lot of small numbers and then add them up, okay? This method is actually due to Archimedes, I mean, so long time ago. I mean, probably 2,000-3,000 years. So, yeah. So calculating normal probability is a numerical challenge because there is no closed formula for the integration. And the computation relies on numerical integrations. Fortunately, we have the following result. Now, of course, a lot of these things are now quite, I mean, you don't feel the pain because nowadays you can use your graphic calculator and all this. My age is the dark age. We have to use table, and it's only accurate up to 4 decimal places, and it's only for selected values. Now, but then there is a good news about the normal distribution, because if you imagine you have to have a table for a given choice of mu and a given choice of sigma, then you will have many tables you need it. Before I come to class, I searched our library, the digital library, and the binomial probability book is still in our library, but it is in closed stack. If you want it, the book was published in 1953. I don't know how many pages are there, but it should be put in the museum, I think. People actually do a lot of numerical calculation in the past, and doing numerical calculations is a pain too. Nowadays, you just put it into your computer, but in the past, people have to take care of accuracy, decimal places, and then they probably crunch the number like this, all right? Okay, as it turns out, you only need one table for the normal distribution because you can always recenter it and rescale it, all right? So you center it by changing the mu, so minus the mu, and then you rescale it by dividing the length by the standard deviations. Okay, and because of this, we have, so this is the mathematical proof that it is in this way. All right, this is just by a change of variable. Okay, and the change of variable is spelled out here. Okay, I think you are not interested in this. But this is the conclusion here. This means that we need only tabulate one statistical table for the normal distribution, and this can be done now on just one page, all right, rather than a whole book for different mu and different sigma. And there are other properties of the standard normal, and because of symmetry, bigger than 0 is the same as less than or equal to 0. Okay. I think we haven't introduced the term standard normal, right, here. Okay, let me introduce the term standard normal. First of all, it has to be a normal distribution, all right, and the mean is 0, and the standard deviation is 1. So when you have a normal distribution with mean 0 and 1, this is what we call a standard normal, all right? Why is it called a standard normal? Because all the other normal distributions can be changed back to the standard normal, all right? So this is, it is actually a technical term here, standard normal. And now it is bigger than the mean, and this is less than the mean. So because of symmetry, it is exactly the same area, all right? So as a result, the total area is 1, and if the right side and the left side have the same area, then they have to make it to be 0.5, all right? Another thing is, it's symmetric also in this sense. If you have a random variable that is with mean 0 and 1 and normal, the negative of this random variable is still standard normal, all right? Okay, what it means here, I think part 3 is easier to see in a picture than in a formula. Okay, because we are looking at standard normal, so this is the best I can do. All right, sort of bell shape. So what it's saying is this is Z here. This is minus X. This is your property 3. And a mirror reflection of this number is X. So what it says is this area is equal to this area. What is this area? This area is phi of minus X, and which is the probability of standard normal. They call it Z minus X. And here, this is the probability of X bigger than or equal to X, or this is 1 minus phi of X. All right? So this is how it comes about. Because of property 3, now papers are very expensive in the past. And people try to print as little as possible. Even in journal article in the past, they specify that you don't write a fraction A on top of B because it takes up horizontal, vertical spaces. They would ask you to write A/B. All right, that is this. All right, so this is in the past. All right. So anyway, so this is this. This is part 4 that I'm explaining. All right, and then how about part 3? So this is part 4. And then part 3. Suppose this is X. Okay, this is just saying this probability Z is less than or X, of course, is the same as 1 minus this area. All right? Okay. So, in fact, part 3 is not interesting to me because this is actually true for all random variable. It doesn't really, it doesn't really peculiar to the normal distribution. So property 3 is actually true for all random variable. All right? Okay. Because this is the opposite of this event. So it just follows from our basic probability property. The probability of an event is 1 minus the probability of the opposite event. So this is not peculiar to the normal distribution. It's just saying that because of the symmetry, the left tail and the right tail are the same in that respect. All right. This is where the usefulness of here. If you have just a normal distribution with mean mu and sigma square, this is what we call a standardization, subtracting the mean. So you move the mean to 0 now, and you rescale the thing so that the standard deviation is equal to 1. The normal distribution is being preserved. All right. Now this is not always the case. Suppose if you have exponential distribution, if you move it, then this is not the 0 in the exponential distribution has a very strict meaning. It is the starting time of the instrument. All right. Now another thing is if you have a standard normal, you can always get something that you want. A normal with mean mu and a normal with variance a square. All right. So basically, part 5 and part 6 is telling you how to transform from one normal to a standard normal, or from a standard normal to a normal. So as long as you have a way to generate standard normal, then part 6 is telling you that you, by this linear transformation, you will get a normal distribution with the desired mean and the desired variance. Now, because of the symmetry property part 2, whether you choose A positive or A negative doesn't really matter. Okay, so yeah. Now, this is the kind of table that I suffered when I was learning it. The first thing is, but you have to suffer a little bit, at least maybe for 10 minutes. I mean that we will give you this table for your examinations. Now, we allow you to bring in your graphic calculator. So if you have a graphic calculator, then you can throw away this table. But the thing is, we don't want you to waste money just for the 10 minutes exam part. Okay, I'm not saying that we even have a normal problem. Okay, but anyway, the first thing when you pick up any table, because a lot of textbook will have a table on normal distribution, the first thing is to understand what the entry stands for. So that is why usually they would either have this plot, because the number here actually refers to the left tail probability from minus infinity to this. Now, you probably won't see this kind of table anymore, but NUS used to have sort of official statistical table, and the booklet is actually more catered for hypothesis testing, and so they actually give the right tail area. All right, so so when you use it, you have to watch out for this. Now, some other textbook might not even plot this, but they will just have a little sentence or whether it's left tail or right tail. All right, so you have to watch out for this. The pain of this is that suppose you wanted to find out the probability of, say, say 1.2. Okay, so you have to look for 1.2 here. All right, and that means you don't need to get anything extra. So the probability would be 0.8849. All right? Is it clear? I'm not sure whether this is better. Okay, I think this is better. Now, suppose I'm interested in calculating phi of 1.2. Then, of course, we know the number is from here. So this will be the number that I get. So I look for 1.2 here, and so this is the number that I want. All right? And suppose you want not 1.2, but 1.23. Then you have to have a corrections of another 0.03 here. So you would have to look for here. All right? Okay. It's getting a challenge to me because my eyesight is not as good as before. All right? So it's this. All right? Now, you will ask, I mean, what if I want to have 0.1234? Then the answer is too bad. I mean, it's not in the table. Then what if people are really fussy, then they just do an interpolation here. So this is it. But this is live during my time. But of course, you won't suffer this kind of thing anymore. Okay. Now, as in passing, this is this number, 0.8413. So what it means is on the right-hand side of one standard deviation will be 0.16. All right, and the other part would be 0.16 as well. So the total area outside one standard deviation would be 2 times 0.16, which is something like 0.32. And that is why we get the 68 rule for one standard deviations here. Okay, so this is this, all right? So I think it's getting, very repetitive. I suppose everyone has done the normal, right, in your, before you come to here, right? Is it normal to assume this? All right, so, yeah. Okay, so the normal distribution, I think, in my calculations. Now, nowadays, you don't even need to standardize it anymore. Because as long as you are willing to type in a little bit more, type in the mean and type in the standard deviation, then this is the cumulative distribution up to 80, all right? So this is it. And so if you want the numbers to be sandwiched between 47.5 and 80, so this is what you will do here, all right? So this is it. I think this is, now this is not an academic example. I was told that this is actually one of the very small argument in a case, in a legal case, all right? The legal case is actually the husband is suing the wife that the child is not his, all right? Because he knows that he is away 290 days before the birth of the child and 240 days before the birth. So during this 50 days, he was not around. And if the normal pregnancy is 270 days and sigma is equal to 10, this is quite well studied, but I was Googling it before I came to class. There are articles starting to say pregnancy is now getting a bit shorter, at least in the US data. So instead of the usual 40 weeks, now it's 39 weeks. So we do not know why. Or we are getting more and more intelligent, so we don't need to stay in the womb, so we can come out 1 week earlier. But anyway, we don't know. But this was the data at that time. So basically, here in this situation is if it says it's the defender, probably is the defender is the wife, defending that the child is still my husband's, all right? And the pregnancy happened to be either very long, that means that they have the relationship before the man travel, or the pregnancy is very short, that was the relationship started, or whatever it is, started after he came back, all right? Now, of course, I feel that there are other things that the defense hasn't quite put into the argument, because one should also put into the menstrual cycle of the woman, and that would also be another kind of calculations that we can put it into. Now, because whether they have relationship before the trip or after the trip, it's just between them. So there is unlikely to have any witness to testify. But anyway, this is just a very nice problem, a practical problem and a real one. All right. So X is the length of the pregnancy. All right, and we assume it is normal distributed, and the mean is 270, and then the standard deviation is 10. So this is happening. The pregnancy actually starts before the man started the trip. So that means this pregnancy is unusually long, longer than 270 days. And then this, or the pregnancy actually starts less than 240 days, start after the man came back, all right? Okay, and so, so we have these calculations. And we have this. All right. So the probability is about 2.4%. Now, for the expert witness, in probability calculations, this is where we will stop. All right. And now it's up to the both lawyers to argue whether 2.4% is small or is not small. Now, if it is small, then the argument would follow that since this is small, it is unreasonable to assume that the pregnancy, the husband is actually the father. All right? But if the other lawyer argued that 2.4% is not a small probability, it's still likely that such a situation occur. So now we will stay away from it. So it would be up to them to argue until the cow come home. All right? Okay, this is actually how it can be done. This is, we calculate this probability, that is the normal one. That is during the absence of this man. And we calculate the probability here, but this is not what we want. We want the opposite of this. So this is it. Now, in a lot of examinations, a certain model is the bell curve, all right? And now, when we come to the central limit theorem, I will make some comments about why is it reasonable to model an exam paper result in a normal distribution. All right. So an examination is often regarded as being good in the sense that of determining a valid grade spread for those taking it. If the test scores of those taking the approximation can be approximated by a normal density function. So in other words, a graph of the density frequency of the grade score should have approximately the bell shape. So here people usually plot a histogram of the scores, of the actual scores, and then visually judge whether it is bell-shaped. All right? Okay, but then now suppose it is a normal curve, a bell curve, and now how do we assign the grades? This is not what we do, all right, but close, all right. A to those whose test score is greater than mu plus sigma, and B to those between mu and mu plus sigma, and so on. So meaning that if you are one standard deviation above the average, according to this example, it will be you will be given an A. If you are above the average, but within one standard deviations above the average, you will be given a B, and so on and so forth. So all right. So so this is it. So to get the percentage of A to be given would be this probability. You can actually start from doing this if you have the software. You don't need to do this. You need to do this only when you are looking the problem up from a statistical table. So you don't, if you use a graphic calculator or some Excel or whatever, you can just move from here to the answer, all right? So about 16% of the people will get an A, and then about 36% will get a B, and C will be symmetric, and D would be this. And then an F grade when the students score 2 standard deviation below the average. So it's about 2.3%. All right. Now, this is just a convenient place to introduce the term quantile. But it doesn't mean quantile has to stay with normal distributions. All right. So, I think the person who is preparing the slides is quite careful. It didn't say what is the distribution of this. All right. This is true for whatever it is. So the situation is this. I wanted to compare the two situations. Okay, I'm assuming I'm drawing it under the assumption that it is a continuous random variable. So as a result, I have a density curve. To make sure you don't think that it is a normal distribution, I make it quite skewed. All right. So one of this is give me an x. I want this area. This area is f of x. All right. So the plot here is fx of x. Okay, so this is our usual problem. We are interested what is the probability when it is x. But then there are other situations that we are interested. If we want say we wanted to find out what this number is, if I specify this, say let's say 0.9. I want to specify the area, and then I ask a reverse questions. I want to find out this number. And this number is called a quantile. To specify what the quantile is, this is 0.9 quantile. All right, of this number. So in other words, so suppose you have the function. So now you want to find out this number so that this is 0.9. So you are solving you are basically taking the inverse of the function. Now for, say if x is exponential distribution of lambda, so this would be easy because e to the powers minus lambda question mark would be 0.9. Okay, it is not small enough. Okay, so for exponential distribution, I want to find out this number so that it would be 0.9. So, but we know this. So this would be 0.1 equal to e to the power minus lambda question mark. Then you take the logarithm. You are supposed to know the lambda in order to solve it. Now this is easy if you have something that you can express the distribution function. But for normal distribution, as we have mentioned, we don't have a closed form for the distribution function. So in the past, people construct the table like this, and then they have to go back and look for the places where they miss, and then they do further subdivision and then calculate the number. So this is actually still done, but it's done in the computer, all right? And when, I mean, maybe 20 years or maybe 25 years ago, even some software are having this. The software is not fast enough. So what they do is actually they save the table into the software. And so when you are asking it, the software is just looking up the table for you. But now, because of the calculation is so fast that they don't even need to save it in the memory. They just calculate it on demand. All right. So this is the number that I use a question mark for it. Here in the notation we have just to indicate it's a set, but it is a function of Q. So we have this. So it is sometimes of interest to look for the quantiles of the normal distribution, like the following examples. All right? Okay, so I will take a few minutes from you guys. Suppose the height in cm of a randomly selected individual has 170 cm. So I was saying the mean is 1.7, so I'm pretty accurate. But I exaggerate the standard deviations. I told you earlier it's 10, but it is 5. But I don't know whether this is real anyway. So the probability that the height of the randomly selected individual is between this. So we are looking for the area, and so that would be depending on the distribution function. All right? But we are interested in the quartiles. All right? the 25% and the 75%. So we specify the area to be 75%, and we want to find that number. All right? Okay. And so this is how it is done. So in the past, people do this because the quantiles are useful for a lot of situations, basically for hypothesis testing and the construction of confidence interval. So they need that, all right? Because otherwise, you have to go back to this table. In the old days, people save paper by only giving you this table. Then you have to look it up, which one is close to 75%. Okay, so it's a test of eyesight. All right, so look around, and then you have to go back and do interpolations. Well, life is different now. Okay, so a bit kinder would be people give you this kind of quantile table, so give you the corresponding ZQ for normal distributions. But this is actually things of the past, and we are interested in 5%. Now this is crucial because this is usually our 5% hypothesis testing, especially we are testing against one-tail test, all right, in normal distribution. And this is corresponding to a two-tail test, all right, when this is 95. All right, so this is how you get it. So this is 1.645. This is where the number you use very frequently for confidence interval. And so I need 0.5 here, and I want it to be 0.75. All right? Okay. So, but here this is very easy. For normal distribution, the stem is still normal, but this is quantile, so it's a Q here. And you want it to be 0.75, the third quartile, and so this would be this, all right? So, yeah, so life is just so much easier now, all right? So how about 25 percentile? First of all, we expect the number to be negative because up to 0 is 0.5. So it has to be on the left-hand side of 0.5, all right? And actually it's symmetrical here, all right? Okay, so this is the R code. So maybe I'll stop here. It's not ending yet. So maybe I'll stop here. Yep. So we'll pick up from example 9 next week. All right.